So the purpose of this lecture is to go over a couple of the homework problems that you'll be responsible for knowing about on the exam 5. So this is your homework assignment on AC and phasors, and we're going to start by looking at problem 9.1. Now I want to point out that you do still need to do this homework. You need to do it on your own paper. You need to do it in an organized and easy to follow fashion, and you do need to upload it on Blackboard. But I am going to step you through how to do the solutions. Some I'll actually do, some I'll actually give you an overview of how you would do the solution. So the first thing we want to look at is we want to look at this sinusoidal expression, 40 times cosine of 100 pi t plus 60 degrees. So this question concerns some basic definitions. The first you're asked is, what is the maximum amplitude? The amplitude can always be found right here. So 40 volts is the amplitude. The next thing you're asked is, what is the frequency in hertz? So to find the frequency, you come up to the function and you look at what is multiplying t. That is not frequency in hertz, that is frequency in omega. So omega here is equal to 100 pi radians per second. And F, the frequency in hertz, is 100 pi, or omega, divided by 2 pi. So that would be 50 hertz. And hertz also has units of cycles per second. So F is omega over 2 pi. So that would be the answer to B. The answer to C would be omega. You're asked for the phase angle in radians and degrees. The phase angle phi can be read directly by what is here in this position in the function. So phi is 60 degrees. Remember that the ratio is that 60 over 2 pi, or sorry, 60 over 360, a full rotation, is equal to phi in radians over 2 pi. So to get phi in radians, which is the answer to D, you would take and simplify this, so it would be 2 pi over 6, or pi over 3. In AC, it is perfectly fine to leave phase angles that are in radians per second. In terms of pi, that's fairly commonly done. Okay, what is the first time after t equals 0 that V is equal to negative 40 volts? So what we want to do there is we want to say 40 cosine of 100 pi t minus 60 is minus 40. And so cosine of 100 pi t minus 60 is minus 1. Now we know that the cosine of some angle theta is equal to minus 1 when theta is equal to 180 plus or minus 360 times n, any integer. So in other words, it's 180, it's 540, and so on. Now they asked us for the first time, so we would take the smallest angle. So we want 100 pi t minus 60 degrees to be 180 degrees. So 100 pi t is 180 plus 60, or 240 degrees. And now the problem we have is that this is going to be in units of radians, and this is in units of degrees. So one or the other has to change. So what you want to do is you want to convert your degrees to radians. So T will be this angle in radians, which is 240 over 360 times 2 pi, and then all of that divided by 100 pi. So I'll let you redo that and figure that out. We're also asked, the sinusoidal function is shifted 10/3 of a millisecond to the right along the time axis. So what is the expression for V of t? Okay, so first of all, a shift to the right is a negative phase. So 10/3 of a millisecond is the actual shift that you want. Omega is, let's go back up, it is 100 pi radians per second. So a 1/10 millisecond shift times 100 pi radians per second gives you, if you do some simplification on the milliseconds, it should give you pi over 3 radians, which is pi over 3 is 60 degrees. So because it moves to the right, when a phase moves to the right, that's a positive phase, that's a negative phase shift. So the cosine of 40 cosine 100 pi t, the original phase angle was minus 60. We now get that we're going to have to introduce an additional negative 60 degrees to shift that to the right by the designated amount. So we'll need to have minus 120. That's our new function. Okay, and then finally, we're told what's the minimum number of milliseconds that the function must be shifted to the left if the expression for v of t is 40 sine of 100 pi t. Well, to the left shift would be the same. So we're basically, and let's see, notice first of all that this is sine. So we need to do a conversion so that we're comparing apples and apples. So the first thing you would do is you would convert the original cosine function to sine and see what that gives you. And I'll let you look up the relationship between cosine theta is equal to sine of theta plus or minus what. So you need to first convert to sine, and then you'll have a phase angle. So you'll have 40 sine 100 pi t plus some phase angle phi. Okay. Now, given that phase angle phi, you have to figure out how to make that 0. So you'll do that exactly like you did the previous step. You'll just basically set omega t equal to 0. Sorry, that's not quite right. You want your phase angle to be shifted by this amount. So you set omega t equal to the phase, solve for t, and then figure out whether it needs to shift to the left or to the right to get to 0, and that'll tell you how many milliseconds in that time shift and whether or not it's and whether or not it moves to the left or right. So that's that. And let me now look at a couple of examples from question 1. And so here we want to talk about phasors. So I'll review a little bit the concept of phasor as I work this problem. So as you know, let's look at 9.11a. So as you know, when you have transcendental functions, also known as sinusoidal or trigonometric, there are lots of rules for combining those. There's, double angle formula, just lots of rules, and the trig can get pretty dicey, especially if things get a lot different. So what we need to look at is, first of all, in this chapter and in circuits 1, we're always dealing with single frequency signals, and we always want to deal in the cosine domain. So we've got this expression, and it's trigonometric, but notice the frequency omega is 500 radians per second in both of these. So what that means is, because it's a single frequency, we can use a conversion into the phasor domain. Now let's recall what the phasor domain is. Remember that e to the j theta is cosine of theta plus j sine of theta, where j excuse me, is defined as the square root of -1, so it's imaginary. So the real part of this complex number, e to the j theta, is cosine theta. So what we can do is, for these cosine functions, we can convert that to the phasor domain by removing the time dependency, working only with the amplitude and phase, and then putting the time dependency back in the end. So what's required for this is, first of all, everything has to have the same omega t, and we have to have a cosine function. Once we have that, we can write y as a phasor, which is the magnitude 50 times angle phase, plus 100 and the angle of that phase. Okay, this angle of 60 is shorthand notation for the real part of e to the j 60 degrees. Okay, so it's just a shorthand, writing it as phase or angle form. Okay, also, remember that a complex number, c angle theta, can be written as c cosine theta plus j c sine theta. And so if you're adding complex numbers, this is what is known as polar form. It's difficult to add in polar form. So what we want to do is we want to say that's 50 cosine 60 degrees plus j 50 sine of 60 degrees plus 100 cosine of minus 30 degrees plus j 100 cosine or sine of minus 30 degrees. And so now what we're going to do is we're going to do the calculation, and then we're going to combine real parts and imaginary parts. So the cosine of 60 is 0.866. So this is 50 plus j 50, and the sine of 60 is 1/2 plus 100. The cosine of 30, did I get that backwards? Yeah, I got that backwards. The cosine of 60 is 1/2, and the sine of 60 is 0.866. Yeah. Because the cosine of negative 30 is 0.5, and no, it's 0.866. I keep doing that backwards. And the sine of negative 30 is minus 0.5. Okay, hopefully I got my sines and cosines right. Okay, so I have 25 plus j 43.3 plus 43.3 plus j 0.5. And sorry, that is not 43.3, that is 86.6. And this is not 0.5, it is 50. Okay, so adding together comparable terms, the two real parts add together. So that's 25 plus 86.6 is 111.6 plus j, and let's see, this one was actually negative. So I've got a negative 50 and a plus 43.3, so I've got plus j times minus 6.7. Okay, so this is rectangular form for those two functions. Now what I need to do is I need to get that in magnitude and phase form. So the magnitude is the square root of the real part squared plus the imaginary part squared. And I'll leave that for you to calculate. The phase is the inverse tangent of the imaginary part over the real part. Okay, so the solution, and what do they call that? They call that y. Y is equal to whatever that magnitude is times the cosine. You put your time domain back in, 500t, and then you fill in whatever this phase is, and that should be in degrees. Okay, so that's how we do that one. B and C are exactly the same. D is exactly the same, except omega is a variable. On B and C, you have a sine term. So on part B, you have 100 sine 377t plus 150 degrees. And so if we play with that, you need to convert that to 100 cosine 377t plus 150. And to go from sine to cosine, you either add or subtract 90 degrees. So let me just look that formula up. Sine to cosine. Conversion. Just want a simple formula. Here we go. The sine of omega t plus phi is equal to the cosine of omega t plus phi minus 90. That's what I thought. I just wanted to be sure. Okay, so then you basically would combine that to get 100 cosine 377t plus 60 degrees. And then that would be what you would substitute for that sine function in the problem. So having worked one of those out, I'm going to leave the other three available for you to practice. And let's look through this assignment and see if there's anything else that I want to address right now. At this point, for what is going to be covered on your exam on Tuesday, that's probably it. So let me come to the end of this. Actually, let me open a new blank document. Let me open a new blank document and let's just review really quickly. So I have some v of t equal 10 cosine 20 pi t plus 30 degrees. The phasor for that is written like this, and it is 10 angle 30, which is shorthand for 10 e to the j 30. And then applying Euler's rule, that is 10 cosine 30 plus j 10 sine 30. So this is polar form. This is rectangular form. So polar form, as a general rule, would be some complex number, and we'll go ahead and call it f. It would be written as some magnitude c e to the j theta. And rectangular form, f, is a plus jb. You can draw a picture of that on the complex plane. So here's the j-axis, or the imaginary axis, and here's the real axis. And you can draw it one of two ways. You can either come over a unit of A on the real axis and B on the imaginary axis, find that point and draw it like it's a vector. Or you can realize that theta is the angle that it makes with the horizontal axis, and C is the length. So to go from one to the other, C is, and I'll draw the absolute value just to indicate that it's a magnitude, the square root of A squared plus B squared, and theta is the inverse tangent of B over A. Okay, and to go the other direction, you would just apply Euler's relationship. So this is from polar to rectangular. This is from rectangular to polar. Now, as a general rule, it is easier to do addition and subtraction using rectangular, and it is easier to do division and multiplication using polar. So we just showed you an example of addition using rectangular coordinates. Let's go back and see if we can't get a new page. And let's show you division. So suppose we have two complex numbers, 30 angle 20 divided by 50 angle 90. So basically what you do is you take the magnitude parts and you just divide that like it's a fraction. So 3/5 or 0.6. You take the angles in the numerator and subtract the angle in the denominator. So that division would be 0.6 angle minus 70. Okay, so that's that. And then let's see, suppose you had multiplication, 30 angle 20 times 2 angle 15. Okay, in that case, you multiply the magnitudes, so you would get 60, and you add the angles, so 60 angle 35 would be your result there. Okay, so being able to do these kinds of operations is inherent in the second problem on your homework assignment. I did not give you specific practice problems on this because it's really something you're kind of supposed to know from pre-calculus. If you don't know it, please review that, and I think I did post some review things on the website for you to look at, and you can always go back to Khan Academy or Wikipedia, ask for multiplication, division, addition, subtraction of complex numbers, and you'll get a lot of examples if you need remedial work on that. But that is something that you do need to know how to do for your exam. And also conversion from a signal, from a function in the time domain to its phasor equivalent and back, which we showed in the previous example, that once you've done all your calculations and you have your magnitude and you have your phase angle, you've got the same frequency in your cosine function. You just plug the magnitude back in the magnitude part and the phase back in the phase part, and that gets you your function back in the time domain. So the point of phasor analysis of AC circuits is to take a function from trigonometric into an algebra kind of function. So if you think about it, when you take time derivatives in the time domain. You know, v is LDI/dt and I is VDC/dt or CdV/dt. When you do that, you're going to generate all sorts of sines and cosines and everything, and just have this mess of transcendental functions. Whereas if you change to the phasor domain when you're analyzing an AC circuit, you can analyze it just like a DC circuit. The only difference is you'll have complex numbers in your analysis. So for next week and for the next exam materials, you will need to start converting circuits from the time domain to the phasor domain. But for exam 5 this semester, your topics will be RL and RC circuits, and using that general equation and the lecture that we posted on, suggested homework, guidelines for that homework. So it'll be that and what we have covered today. So problems 1 and 2 out of your homework assignment. The remainder of the stuff on phasors and circuits will be taken up in exam 6. So hopefully that